SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 2, that is Vapor Power System Part 2. So, in this lecture we will start a new topic, and that is nothing but your steam nozzles, and the steam nozzles are the essential components for steam turbines. But in this lecture we are going to study the theoretical aspects of steam nozzle. Before you start that thing, the theoretical component consists of the thermodynamic aspects of the effect of area change and flow properties with respect to thermodynamic parameters. Now, based on this we will try to see that how the flow properties are going to be affected when there is a area change, and this change in area, in our term we call this as a shape of the nozzles, how the shape of the nozzles we have to design. While talking about the shape of the nozzle, then we will do some theoretical treatments of nozzle shapes, finding its optimum configurations, and when we design such nozzles, what should be the critical pressure ratio. These are the important topics of this today's lecture. So, let us try to understand what is the effect of area change and the flow properties. Ideally speaking, we are talking about the area change with respect to nozzles. So, in our previous studies, when you dealt with impulse and reaction turbines, we have seen that nozzles are the integral components. For example, in a single stage impulse turbines, nozzles feeds the steam for rotation of the blades. Then that is happens in a single stage turbine, and when you go for compounding also, a single nozzle supplies the steam to all the moving blades, and they are arranged in a particular fashions. So, that is called as a Curtis turbines or velocity compounded impulse turbines. Now, moving for the pressure compounding impulse turbine, that is reactive turbine, where we have the each of these moving blades needs a separate nozzles for feeding of steams. And in most important fact is that in all these impulse turbines or all these arrangements, what we see is that most of the pressure drops. If you can see this figure, you can see here that pressure drop takes only in the nozzles. Here also pressure drop takes in the nozzles, same thing here. So, at the cost of pressure drop, we can see the increase in the flow velocity, and of course, when there is a pressure drop, the enthalpy also drops. So, this is what happens is that all these enthalpy drop or total enthalpy of the steam, drop in the total enthalpy is compensated through the pressure drop. But however, when you do this expansion in the reaction turbines, there also, although there is no separate component of nozzle as it is, rather they have fixed blades or guide vanes that takes care about the pressure drop. But most important fact is that the passage of those fixed blades are such that they perform a nozzle actions. Nozzle actions I will explain in the subsequent slides. It is nothing but flow has to expand, at the same time the velocity must increase and pressure must drop. So, this is what we call as a nozzle actions, and this can be achieved with suitable change in the area of the passage. So, either you can have a separate arrangement for that, what we call as a nozzles, or we can have same nozzle actions we can perform by designing the flow passage. So, in any case area change is the driving factor. So, this is what I have explained here. For impulse turbines, nozzles are the integral components. For reaction turbines, nozzle action is more important and they are achieved through fixed blade or guide vane arrangements. Now, let us try to understand more theoretical aspects, how what is a nozzle, and with respect to our situations, like when we talk about steam, superheated steams and the flow expands, and in any case the flow is typically either liquid or steam or vapor, and it is mostly falls in the incompressible range. So, for that, if such a fluid has to expand, what should be the shape? So, this is the main theme of the discussion for in today's lectures. So, by definition what we can say that nozzle is a duct of smoothly varying cross sectional area in which a steadily flowing fluid can be accelerated by at the expense of pressure drop. So, this is first thing, but at the same time this pressure drop means in this case why the pressure drop has to happen, because steam is in the superheated conditions of very high pressure and temperatures. So, the need of the nozzle has many applications in practice, where we require high velocity of stream of fluid, and for that nozzles are the best choice. So, we have steam, gas turbine engines, jet engines. In fact, in the jet engines nozzles gives the adequate thrust at the expense of pressure, because it accelerates the flow and at the same time the reaction force from the exhaust gives the necessary force for the body to or the jet engines to fly. And in the category of opposite action, that is when the fluid is decelerated in the duct causing the rise in the pressure along the streams. So, that is called as a diffuser, and typical application includes that we have the passage that involves centrifugal compressors, ramjet engines, where the intake systems are designed that flow has to decelerate and causing the rise in the pressure. Now, our analysis will try to stick into a one dimensional flow, and while talking about one dimensional flow, we can say that we can have a converging passage where the area decreases along the direction of the flow, or we can have a diverging passage where area increases along the direction of the flow. And of course, we do not look into the effect of frictions, which is ignored. So, it is a frictionless flow, and we also have some assumption like the fluid velocity remains constant at the mean value, although the area changes, but when you take the fluid velocity maybe at any particular sections, we take this mean value along this particular sections. That means, at each sections we have one value of velocity. So, that is the assumption we make. Now, let us try to understand this same concept with respect to the Mollier diagram, because most of our analysis is referred with respect to Mollier diagrams in which the flow expands. When there is a flow expansion takes place from higher pressure to lower pressures, and you can use this one dimensional equations where enthalpy remains same at two locations, and at one particular location when the fluid starts with 0 velocity. So, the total enthalpy is nothing but the static enthalpy. So, basically speaking, that initial state we have the total enthalpy which is available in the fluid, and it expands to certain pressure. Now, during this expansion process, and if you assume this expansion process to be isentropic, then what we see here is like this. If you see that the flow expansion takes place from 0 to 1, then that means the arrow that shows towards the bottom, then what is going to happen is that your velocity will increase and pressure will drop. That means, we are going for decreasing the pressure, but at the increase in the velocity, or the fluid gets accelerated. Now, if you go from 1 to 0, that means fluid is decelerated and the pressure increases. So, this is the very basic theory for nozzle actions and diffuser actions, and this thermodynamic behavior can be replicated by designing this flow passage. Now, in either case the passage can be converging or diverging. Whether the expansion has to take place or compression has to take place, or in other words whether this diverging passage will behave as a nozzle actions, or these diverging passages can also behave as a diffuser actions. So, all this it depends on the nature of the flow. That means, if the expansion has to happen, that means if it is a nozzle actions, then the fluid must accelerate, velocity must increase, pressure must decrease, and if the flow is incompressible, then we will have a we will end up having a converging passage. If the flow is compressible, then we may have a diverging passage. So, this depends on whether initial flow is subsonic or supersonic. So, that means, if your initial flow is supersonic, a converging passage will act as a diffuser action, or when the fluid is initially subsonic, the converging passage will act as a nozzle actions. But however, our philosophy that will, since we will be dealing with incompressible flow and initial situation is always subsonic, then our main focus will be the converging passage. So, in the other side of the story, that we can get the compression process in the molecular diagrams, and the flow compression along the path involves increase in the pressure with change in the area of the flow passage. So, in the process of compression, the static enthalpy increases and the flow velocity drops. So, the diffuser action is just opposite to the nozzle actions. So, this is not part of our discussions. So, just for the sake of curiosity, that flow passage or area, how the area change affects the flow properties, in that context this analysis is more important. Now, whatever we discussed, if you can summarize, that when a fluid is allowed to enter a passage in which area can change, then we can achieve compression or expansion of the fluid in the direction of the flow. If it is an expansion of the flowing fluid, then we call this as a nozzle actions. If it is a compression of the flowing fluid, if we call it as a diffuser action. Then let us try to understand what should be the shape of the nozzles. All this depends on the area of the passage. So, to understand this concept, let us try to think about a stream of fluid at certain pressure P1, enthalpy H1 and flow velocity C1, which enters in a duct. For the time being, let us stick to this converging passage, in which we have P1 and enthalpy is H1 and velocity is C1, which enters in the duct. So, we can apply the steady flow energy equation at any section Xx. So, we can mark it as any section Xs. We need to see that how the pressure is going to, or the flow properties values, how it is being detected at this section Xx. Or we can say whether it is since it is nozzle actions, the pressure has to drop, that means how that pressure falls along the length of the duct. So, for that reason we consider the steady flow energy equations, where the total energy at the inlet stage is that m into h plus c square by 2 plus gz, that means enthalpy plus kinetic energy of the flowing fluid plus the elevations, then heat transfer and work transfer. For the time being, we are going to neglect this heat transfer and work transfer terms. Now, if you see and if you have the same mass flow rates, so it gets cancelled, and then we arrive at an equations where which says that h plus c square by 2 is equal to h1 plus c1 square by 2, which means h1 plus c1 square by 2 is your inlet, and h and c at any values referring to section Xx. So, this gives an expression that for at any Xx, any sections, we can arrive at the what is the velocity of the flow, and that is c is equal to twice times entire square root of twice time enthalpy difference plus C1 square. Now, let us try to understand the same concept in a different philosophy, or if you can represent in a graphical figure. So, try to understand this particular equations. One is C is equal to twice time H 1 minus H plus C 1 square entire square root, this is one expression. Other is mass flow rate, that means if you can see mass flow rate any cross section is constant. So, that means if from this expression we can say m dot is equal to rho A C, or we can say m dot is equal to rho is 1 by specific volume times A into C. So, this gives an expression that is A by m dot is equal to V by specific volume by C. So, when you put C expressions from here in these equations, we have a relation that is A by m dot, that means area per unit mass flow rate is depends on the specific volume of the fluid, enthalpy difference and the initial velocity. So, for the time being, if you just neglect that initial velocity component to be 0, so basically it is depends on the specific volume and the enthalpy drop. Now, let us try to understand these particular things with respect to these expressions, that if you take the two sections, that is section 1 and section 2, and in these sections if you try to plot this particular curve, that means if you say how area varies with pressure, then how velocity varies with pressure, and how specific volume changes with pressure. And remember, we have fluids, we have using either it is a steam or a liquid. So, we see that the graph that detects in a generic graph that detects says that with decrease in the pressure, that means your pressure decreases, we have performed the nozzle actions, with decrease in the pressure your area drops down, that means area drops and to a particular value, then further it increases, and the velocity continuously increasing, that is anyway that is our expectation, velocity must increase with the pressure must drop. Then your specific volume in the beginning stage it is normally there is not much change, but after that specific volume suddenly increases. So, this gives an indication that but the rate at which the change in the area, the change in the area is often detected by rate at which velocity is increasing or rate at which specific volume is increasing, depends on this. So, the dominance of velocity and specific volume also detects the area change. So, what has been seen here in a closed loop, that we can see that from section 1 to 2 it says that area, a closed loop says that when area decreases initially and reaches to a minimum and then increases again. So, area decreases initially and to a minimum value, then further increases, that means this is the minimum area. So, if I say this point gives the area, minimum area, and after that it again further increases. So, this decrease part is often detected by the rate at which velocity is increasing and rate at which the specific volume is increasing. In the initial part, if you see here that the when V increases less rapidly than C, then area decreases. When V increases more rapidly than C, then area increases. So, this decrease in the area depends on the relative dominance of area, velocity and specific volume. And because of this reason, we have land of having a minimum section, and that minimum area is known as the throat of the nozzles. Now, referring to diagram here, so from these initial things we can say that the throat is the minimum area, and any other thing, that is throat refers to minimum area. Another point, if I recall, that m dot is equal to rho A C, and when you say A by m dot will be 1 by rho times C or specific volume times C. Now, from this expression you see that when C is very high or C close to 0, means A goes to maximum, that means A goes to infinity. So, this word infinity terms here, that when your initially, that is the assumption in most of the cases we say that initial velocity at the nozzle inlet is 0, by assuming the fact that we start this with a very larger area and suddenly drops to a minimum value. So, this sudden drop in the area gives you the fact that your C1 goes to 0, and with this concept the shape of the nozzle is designed. And so, the most important point is that so we in some sense we get that what should be our inlet shape and what should be our outlet shape, and this expression gives you the throat of the nozzle, what is the minimum area. So, this analysis or these mathematical expressions are now sufficient to analyze further to quantify what happens to velocity and other parameters. So, having said this, we say that in most of the practical applications, velocity at the inlet of the nozzle is negligibly small in comparison to the exit velocity, that we can see from this equations that when C is higher, A is larger. That means, in most of the cases the nozzles are shaped in such a way that nozzle converges rapidly over the first fraction of the length, and this is where this is the first fraction of the length where nozzle you can say converge rapidly, and we then we arrive at the minimum area, and from there the diverging action starts or passage starts. Now, in this nozzle, if you say we are using a perfect gas where we can assume that enthalpy, for example, for the time being if you analyze that you are expanding a gas or a perfect gas, the enthalpy terms can be represented in terms of Cp times T, and we can use these equations of perfect gas, that is PV is equal to RT. Then the area per unit mass flow rate can be expressed in this fashions by replacing H in terms of Cp and T, then we can do this some mathematical simplifications. Then we can recall our isentropic process for a perfect gas between pressure and temperature relationships. Now, if you assume that pressure ratio, that means P stands for any arbitrary section XX, so where the properties values are detected by pressure, temperature, specific volume, speed and flow velocity, and inlet conditions are specified as P1, T1, specific volume 1 and C1. So, putting this we can find the area per unit mass flow rate by these expressions, and we by incorporating this here like the temperature ratios from this expression in the form of pressure ratio, we arrive at an expressions, that is A by m dot is equal to Cn, Cn means it is a constant for a given inlet condition, divided by square root of x to the power 2 by gamma minus x to the power gamma plus 1 by gamma. Now, here this expression will give you a conditions for minimum area would be by differentiation of d by dx of A by m dot for this parameter, and after differentiations we find that x is equal to twice by gamma plus 1 by to the power gamma by gamma minus 1, and this x is nothing but your P by P1. So, in other words it says that any arbitrary conditions pressure is detected with respect to its initial condition P1. Now, if this is the conditions for minimum area, and when you have a minimum area, which means that we will have a maximum flow rate which will come back later, but for this minimum area conditions, and this is nothing but when we have a minimum area means it is at the throat condition, that means we are referring this minimum area means at the throat, and at these conditions the values are defined with its critical parameters. So, we can find out the critical pressure ratio as Pc by P1. So, we can get it from this expression by putting x is equal to twice by gamma plus 1 to the power gamma by gamma minus 1. We can find out the critical pressure ratio. Once you have the critical pressure ratio, you can as well find out the critical temperature ratio. So, means here critical condition means we have a minimum area, the conditions are PC, TC and specific volume at C and flow velocity Cc. So, this is the conditions for minimum area situations. Now, putting gamma is equal to 1.4, that is for air, we get the critical pressure ratio Pc by P1 is equal to 0.5283 and temperature ratio Tc by T1 is equal to 0.833. So, based on these minimum area conditions, we are now in a position to define the terms like critical velocity. So, the critical velocity is the velocity at the throat of a correctly designed convergent divergent nozzles. Now, why I say convergent divergent nozzles? In our previous analysis we say that area decreases initially and then increases further. So, by putting this concept, we say it is a initially it is a convergent, then it is a divergent nozzle, when the pressure ratio of the nozzle is the critical pressure ratio. Now, here one of the main assumption is that we are looking at the liquid, or when the specific volume of liquid is constant over a wide range, since then so therefore, the nozzles for liquids is always a convergent, and wherever we have minimum area, so the flow is called as critical conditions at high velocities. So, the critical velocity is the velocity at the exit of a convergent nozzle when the pressure ratio across the nozzle is at critical pressure ratio. So, this is what the basic definition of a convergent nozzles or convergent divergent nozzle. So, we have already derived this expression, that is the velocity of the flow at any section x x, that is C. Then from this we can find out the critical velocity at the throat by putting this expression here, by putting enthalpy term and neglecting C1 goes to 0. Then from this we can find out what is the critical velocity at the throat, considering the fact that Cp is equal to gamma r by gamma minus 1 and T by Tc is equal to twice by gamma plus 1. So, this is what we say that now when the fluid we think it as a perfect gas, then further relations we can make it that these expressions what we have derived so far, we say it is a this perfect gas situations, and again for the perfect gas one can also define a parameter what is called as a speed of sound. The speed of sound by definition we say it is nothing but a square. By definition we say speed of sound is dou p by dou rho at constant s. Rho stands for density. So, we can write this rho as 1 by specific volume and P v to the power gamma is equal to constant for an isentropic process. Now, if you just simplify this expression and find what is A, we can arrive at that speed of sound also has same relations what we have the critical velocity at the throat. So, we can say that critical velocity of a perfect gas in a convergent divergent nozzle is equal to speed of the sound in the gas at critical temperatures. So, and this speed of sound is very vital when we design the nozzles for supersonic flow, but that is not part of our analysis. We will stop our discussions by considering the fact that we are only bothered about the two things. One is what happens at the inlet conditions, where typically C1 tends to 0 and initial conditions will be given P1 specific volume 1 temperature 1, and what is at the throat conditions where we have a minimum area, and here area goes to infinity. Here we have minimum area and properties are defined by its critical pressure, critical temperature, critical specific volume and followed by critical velocity, and any other conditions are defined at any section x x. It can be outlet or exit, and that value we detected by any arbitrary pressure P, T, specific volume and C. Okay. So, with this I have explained the basic theoretical aspects for a nozzle, and whatever discussions what we have so far, let us try to understand one particular problem based on the analysis of nozzle. So, the problem statement goes like this, that air at 8.5 bar and 200 degrees centigrades expands in a convergent divergent nozzle into a space which is maintained at 1 bar. The mass flow rate of air in the nozzle is 4.5 kg per seconds. Assuming inlet velocity is negligible with respect to exit velocity, we need to calculate the throat and exit cross sectional area of the nozzles. This is simple clear cut problem of our analysis of discussion so far today. So, before you solve the problems, so let us first try to draw the schematic diagram what this nozzle, how a nozzle should look like. That means, we have section 1, section 2 and this we say it is inlet and this is exit. And here we have this minimum throat. So, since it is a convergent divergent nozzle, we have minimum area. At this condition we have this, of course, we need to have a critical conditions PC, TC, specific volume and velocity of the flow. Now, the flow is your air and it enters at P1 is equal to 8.5 bar, T1 is equal to 200 degrees centigrades, that is equal to 473 Kelvin, and your m dot is equal to 4.5 kg per second, and the exit condition we do not know. Okay, the only P2 is given was 1 bar. We do not know what is T2, we do not know what is V2, then we also do not know what is speed at exit, and what is the question mark we require, that calculate the throat area A minimum and that is required here, and exit area A2. So, this is what the problem statement is above. So, let us, we need to recall that since we have air, we can say gamma is equal to 1.4. We also require information about R, that is equal to 0.287 kilojoule per kg Kelvin, and Cp is equal to 1.005 kilojoule per kg Kelvin. So, this information is required for air. Now, what we need to know is that what is critical pressure ratio, because critical pressure ratio is required when you find out the minimum area. So, we say Pc by P1, that is equal to twice by gamma plus 1 divided by to the power gamma by gamma minus 1. Now, when you put gamma is equal to 1.4, this ratio becomes 0.5283, and similarly critical temperature ratio, we can find out T C by T is equal to twice by gamma plus 1, and this number is twice by 2.4 or 1 by 1.2, and since we have P1 and we know P1, so we can find out what is TC as 200 plus 273 divided by 1.2, and this value is 394 Kelvin, and we also have Pc is equal to 8.5 into 0.5283. So, this is equal to 4.49 bar, and then we know from Pc Tc we can find out what is specific volume, that is R Tc by Pc. R is 287, Tc is 394, Pc is 4.49 into 101,325, that is that will be converted to Newton per meter square. So, this number we get 0.25 meter cube per kg, and Cc is equal to twice time H1 minus Hc square root. So, we can say twice time Cp T1 minus Tc square root. So, inserting this number, we say twice into 1005 into T1 473 minus 394. So, this will give you Cc as 398.5 meter per second. Now, we are in a position to find out throat area. That is AC is equal to m dot into Vc divided by Cc. So, m dot is 4.5 kg per second, specific volume is 0.25, speed of there is flow velocity at the critical condition is 398.5. So, this will give you throat area as 0.0028 meter square or approximately 2800 millimeter square. So, this area, minimum area, that is throat area, is 2800 millimeter square. Then for exit area, we know the inlet conditions. Same way we can use the, since the process can be treated as isentropic. So, we can say T1 by T2 is equal to P1 by P2 to the power gamma minus 1 by gamma. So, all the information as given. So, we can say it is 8.5 to the power 0.4 by 1.4, this is 1.84. So, this will give you T2 as 473 divided by 1.84. T2 is equal to 257 Kelvin. Then we can find out V2, that is equal to R T2 by P2, that is twice 87 into twice 57 divided by P2. P2 is 1 bar, 101325. So, this is 0.728 meter cube per kg. Then V2, then we can find C2 as Cp times twice Cp times T1 minus T2 entire square root. So, that is twice into 1005, T1 is 473 minus T2 is twice 57 entire square root, and this is 658.9 meter cube per kg. Then once you know the C2, then we can find out A2 is equal to m dot V2 by C2. So, 4.5 into 0.728 divided by 658.9. So, this is 0.00497 meter square or approximately 4970 millimeter square. So, this gives our answer, that we got the answer as the throat area of the nozzle is 2800 millimeter square and the exit area of the nozzle is 4970 millimeter square. So, this is all about the conceptual picture of nozzles and its analysis. With this I conclude. Thank you for your attention.